Alright, the purpose of this video is to explain TLC. In this case, TLC stands for Thin Layer Chromatography. These notes, this side, are posted on the website, so you can download those, follow along with this video where I kind of explain what's going on. As I said, it stands for Thin Layer Chromatography, but let's see what that is. What is chromatography? So chromatography comes from the two words of chroma, of colors, and graph, which is writing. So the idea is that we're going to write or graph or view somehow the colors that might be present in a solution, in a mixture of some sort. A lot of times they got started by trying to separate out the colors in like the different kinds of ink or pigments in a substance, but it's used for lots and lots of other things now, which is kind of what we're doing with this biodiesel lab. It's very useful for determining if a substance is pure, or to determine if a substance is actually even what you think it is, without having to use up a lot of it, or burn it up, or do a lot of complicated tests. It's a very simple test, and it usually shows pretty clearly if you've made what you think you've made. On this slide, you can see the idea of where you would separate out colors using a certain using this procedure. In this case, you get the red, the blue, the green, and the yellow, much like a rainbow. When Blackburn and I first made this biodiesel lab, we tried it out ourselves. We made the biodiesel, but we needed to know, did we make biodiesel? Like, how do we even know? We weren't sure what it looked like and that kind of thing. So I remember from my days in college that there was this test, TLC, that would enable us to basically determine not only the purity of our biodiesel, but even if we made biodiesel at all. So the way that it works is you would put a spot of the thing you're trying to test right there at the bottom, the little blue spot, and it sits on this plate. This is the thin layer. This is where it comes from. It's very thin. I've got one right here. They look about like this. They are very, 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 very thin. Not a lot to them. Okay, so you would take this thin layer. You would put a spot of the substance you're trying to test, kind of towards the bottom, and then you would dip it in something absorbent, something another solution of some sort. You can use almost anything. You usually don't use water, but you can use other substances. You dip it in that, and as that substance absorbs up this thin layer plate, it'll pick up that spot of the thing you're trying to determine. And basically, the amount of interaction, amount of attraction that your unknown substance has to this known solvent, as that solvent travels up this plate, that interaction is going to tell you what kind of substance you have in that spot that you just put on here. So a couple of terms to define by this. Your origin is a line at the bottom. That's where you put your first initial spot. Then as the solvent travels up, kind of like that, the solvent front is the furthest that the liquid travels up. So that's going to be at the top. And then the new position of the compound is that new little spot there. Now, you see a couple of measurements here. These are important measurements. This spot traveled 2.1 centimeters in this case. Now, the place you measure the spot from, this is very important, is from the center of the spot. So when you put it on the thing at the bottom, you can see on there, it's centered on that bottom origin line. And then as it moves up, you measure to the middle of that spot. Sometimes spots don't stay as nice little circles. Sometimes they spread out into ovals, or they change their shapes. So you have to try to get to the middle of where that middle of that spot would have been. You don't want the very top of the spot or the bottom of the spot. You want the middle. The other measurement that's on here is how far the solvent itself moved. In this case, 2.8 centimeters. Now, what you do is you just take these and turn it into a ratio. You do 2.1 divided by 2.8. That number would become what's called the retention factor, the RF value. So that RF value is different for every substance depending on the solvent. So when we made this biodiesel the first time, we did this TLC test. We calculated the RF value for our solvent, and got the same number that other scientists had done. So we were able to confirm the fact that we made biodiesel as we had thought we did. Let's go a little bit more into the theory of how this would work. Here's an example. This is a sailboat example. The idea is you have your initial starting point. In this case, we have biodiesel, and we're going to compare it to the vegetable oil. So you oftentimes want to compare it to a known substance or the starting substance and make sure that you actually got a chemical reaction to make something new. Okay, so in this case, we put the vegetable oil down here, and we put the biodiesel boat also down there. So they both have the same starting point. They're both sitting on a substance. In this case, this is silica, a silica plate. It's basically sand. This is called substrate. Those are our substances that we're trying to test. Then we dip it in a solvent. In our case, the solvent is hexane. In our analogy here, hexane acts like the wind. So as the wind hits both of these substances, it tries to push them up with it as it goes. One of these substances interacts better with the wind, the biodiesel does, and the vegetable oil does not interact with the wind, so it basically stays where it is. So the biodiesel gets pushed along closer to the solvent front. You can see at the top where it says front, and the little robot gets pushed a little bit, but not as much. So that's kind of the theory that's going on. So whatever substance is more attracted to the solvent, that substance will move further. That's an important point. The substance that's more attracted to the solvent will move further along, closer towards the top of the plate. Okay. So basically, when we do this with our substance, you're going to get a number. Let's see if this has any numbers on it. Something kind of like this, where you have a solvent front. You'll have one substance that traveled, another substance that did not, and we develop them in iodine. So here's an example of a real one, just like this. Hold it up pretty close here. So this substance shows this is a TLC plate for our two substances. Now on this side right here, this is the biodiesel. Now it's spread out a lot, so it's not necessarily pure. Biodiesel isn't pure. It's got a lot of different chemicals that all count as biodiesel. So it moves all the way up to here. You can see a pretty good spot. And then on this side, you got the oil, which did not move as much. It basically stayed at the bottom and kind of went maybe half as much. So even just without doing any measurements, we can see relatively we made some diesel versus starting with the oil. So that's good news. We actually did get a chemical reaction that we would like. Now, we can take this then and analyze the RF values as well. So we would start with the starting line down here and measure up to the middle of one of the spots. You don't measure to the very top, you measure to the middle of the spot. Take that number, divide it by the distance to the solvent front. I don't know if you can see it in this. It's a little hard to see. It's like a little pencil line right there where the solvent front went to. So you take that number, that's your denominator, and you take your spot, that's your numerator. Divide the two, and you get an RF value. This kind of shows what it would look like on paper. So you would have the retention factor would be a formula, and this formula would be given to you on the test, so don't worry too much about that. It would be the distance traveled by the compound. You would divide it by the distance traveled by the solvent, which will always be the bigger number. So you're always going to end up with a fraction. In this case, or a decimal, I should say. So in this case, the decimal is 0.75. So it traveled 3/4 of the way up the plate. If we were to do the same thing for the oil, it'd be a smaller number. It wouldn't have traveled as far, so maybe it would be 0.5 or something like that. But what you can then do is check, as I said, scientific information. Look for that 0.75 and see if that matches what other scientists get for diesel in hexane. All right, so just quick review. We talked about TLC, thin layer chromatography. The idea is to either separate out a mixture or determine the properties of a substance based on how far it moves. So to do this, we calculate the RF value. We take the distance the compound traveled, divide it by the distance the solvent front traveled, and that number is the RF value. You can compare it to other substances or check it against tables and charts that other scientists have done. In our case, our biodiesel did well. It did what we thought it would do, and the biodiesel would be interacting or attracted more strongly to the solvent because it traveled further. It was more attracted to that solvent, so it traveled with it. Our oil was less attractive. All right, that should be most of the what you need for the TLC, and hopefully this review was helpful for you.